Hello, my name is Matthew Tillmawitz, and this presentation is a brief summary of my thesis. It's on the scalability. It's a scalability analysis of graph neural network architectures on large-scale node classification problems. And in it, we propose new metrics and evaluation frameworks for graph neural networks. Graph neural networks and neural networks in general are known for being particularly resource hungry and intensive. Given recent shortages in GPUs and RAM and their rapidly increasing costs, these kinds of concerns are becoming more and more relevant. As a result of this high resource demand, we find that frequently theoretical complexity does not equate to practical performance due to things such as implementation details, hardware constraints, and model stability that create gaps between real world and theoretical performance. Because of this, a rigorous empirical framework is needed to properly assess model scaling. We propose using controlled graph projections to isolate scaling behavior in addition to more traditional classification analysis. And we will conduct an example of just such an analysis in this thesis. So we propose using a large-scale heterogeneous graph to produce different projections in order to address issues related to testing across numerous different graph data sets. Twibot22 is a real-world collection of Twitter users and is extremely rich data set that encompasses over 90 million different nodes, 170 million plus edges across 4 different node types and 14 different edge types. This allows us to evaluate models in terms of node count by taking samples of the graph, graph connectivity by introducing different projections, which also can introduce different levels of heterogeneity. So we propose 3 different projections on the user space. So all of the nodes will be users with features generated from both the user account information as well as other node characteristics that have been projected down. We begin with our base projection, which only includes follower-following relationships. On top of that, we add our direct projection, which includes reply and quote interactions. And then our final level also introduces co-mention, co-hashtag, and co-retweet interactions. This results in different projections having different levels of connectivity as well as heterogeneity, while getting rid of confounding variables that using other data sets would introduce, such as different feature quality and information gain in the different relationships between nodes. We will evaluate 7 different models. The multi-layer perceptron will act as our non-relational baseline neural network, and then we will evaluate 3 different homogeneous and 3 different heterogeneous models. The graph convolutional network will act as our baseline model in both cases. GraphSage and RGCN are our historically strong performing models. And then SGFormer and the heterogeneous graph transformer kind of represent state-of-the-art models that use complex attention mechanisms and transformers to enhance their networks. These models represent a wide range of architectural complexity, and it'll be interesting to see if traditional scaling assumptions hold, where we would expect the more complex models to be more computationally intensive. We find that node scaling, model scaling in terms of node count, is heavily time-bound, but memory consumption only increases by a factor of 1.4. This is due to a mechanism called mini-batching, which decouples graph size and memory consumption. It's been a common practice for a very long time, but only was recently empirically evaluated in a different study, due to it being seen as an implementation detail, which kind of highlights the importance of these kind of empirical, holistic evaluations in not only graph neural network architectures, but the aspects that are traditionally seen as implementation details. In terms of, in contrast to node scaling, edge scaling is very heavily memory bound, with heterogeneous graphs being significantly more sensitive. This is expected as heterogeneous graphs need to account for the same increased connectivity the homogeneous graph neural networks need to, in addition to accounting for edge types through various mechanisms. However, contrary to expectations, we see the heterogeneous graph transformer actually scales quite well. Transformers in general have a reputation for being very resource heavy in terms of both compute and memory. And we see that while it is it is very resource intensive to run, it actually ends up scaling to large graphs much better than many of the other graphs we see. In terms of classification metrics, all of our models ended up converging. This is largely due to feature quality. Other studies have been conducted that have access to more resources, more computational resources. They've been able to use text transformers to generate better features that lead to more differentiation between relational models. In our case, models hit a ceiling in terms of classification performance at around 0.55, 0.56 F1 score. However, as a result of this performance ceiling, we can use model efficiency to act as a meaningful differentiator. We can see that minor classification performances in the real world may not be worth the expense of, for example, doubled training time in terms of RGCN versus the multi-layer perceptron. Whereas if time is your limiting factor, you might be able to get free, quote-unquote, free performance improvements by conducting more thorough model selection. We can see the heterogeneous graph transformer, SGformer, GCN, and GCNH all take similar levels of training time. However, there is meaningful separation in terms of performance. We propose that a holistic metric to evaluate models is needed, and we call this metric overall efficiency ranking. This is a composite metric and is the normalized aggregation of F1 training time, memory consumption, and throughput. It seeks to frame classification performance in terms of resource costs. More details on the calculation can be found in my full thesis, but we are essentially trying to weigh any improvements in classification performance against increased costs in terms of resource consumption, which is a very real concern for businesses and real-world practitioners seeking to deploy these models. Doing so, given the ceiling in our classification performance, we see the simpler models generally drastically outperform the other models. However, once again, we see the heterogeneous graph transformer kind of bucks this trend and is actually the most efficient of the heterogeneous models, which is a very surprising result and kind of highlights the need for this more holistic resource and efficiency focused kind of evaluation of models. We did see some interesting anomalies while we were conducting our testing, namely, once again, in terms of the heterogeneous graph transformer, we saw non-monotonic memory consumption growth, which is highly unexpected. Memory consumption peaked at 100,000 at the 100,000 node sample and actually decreased at the 250 and 500,000 sample sizes. This is a really, really interesting result and merits further investigation and further research to kind of understand why this model is actually consuming less resources at larger scales. In contrast, we saw unexpected behavior from SGformer. At larger sample sizes, the model would train and eventually achieve a reasonable validation result before experiencing model collapse and seeing all performance metrics go to zero. This is highly unexpected, as the SGformer paper claims strong results on graphs of over 100 million nodes, and no other graphs demonstrated signs of collapse in our study. this kind of highlights the importance of this more nuanced approach to model evaluation, kind of getting in depth and exploring how models react to changes in graph size and structure that have not previously been explored and merit further exploration clearly. So our conclusions for practitioners, those seeking to implement models in production, clearly start simple. Increased complexity has to justify the cost. Edges are very expensive to add, so stick with meaningful relationships that provide value, and heterogeneity is even more expensive. This is a very fruitful area for potential research, seeking a mechanisms that decouples edge scaling or heterogeneity scaling from memory consumption, similar to how mini-batch sampling did for node size. And lastly, architectural efficiency can matter much more than model family. Based on general assumptions, we would have expected the heterogeneous graph transformer to be incredibly resource intensive and not scale. But we saw that that was absolutely not the case. And models and new models and new architectures need to be thoroughly evaluated in an empirical fashion to better encapsulate these kinds of scaling efficiencies. For researchers specifically, we argue efficiency metrics belong in standard evaluations. Controlled projections enable nuanced analysis of model performance on different aspects of graphs in terms of scaling and complexity, and such nuanced analysis can highlight shortcomings or failure situations for specific models. And lastly, published scaling claims need to be independently verified and thoroughly examined. Thank you.